Welcome, everyone. Today we're going to talk about what it means to become an AI native engineering organization. This is not a discussion about using AI as a coding assistant. It's about redesigning the entire software delivery system around AI capabilities. What this means is that architecture, workflows, verification processes, and team responsibilities all need to evolve. The companies that succeed won't simply generate code faster. They'll build systems that allow humans and AI agents to work together safely and at scale. Throughout this session, we'll explore the operating rules, architectures, and guardrails that make that possible. Let's begin by understanding why software development is changing so dramatically. To understand AI native engineering, we first need to understand the scale of acceleration we're experiencing. Historically, productivity improvements in software engineering were gradual. New frameworks, better tooling, and cloud platforms improved output over years. Today, AI changes that curve entirely. A good example of this is how tasks that once required days of implementation can now be generated in minutes. Engineers are suddenly able to create prototypes, APIs, and automation at a speed that was previously impossible. The important takeaway is that code generation is no longer the primary bottleneck. As output increases exponentially, new challenges emerge, and that's what we'll look at next. As AI adoption grows, many teams fall into what is often called vibe coding. Vibe coding is essentially generating code through prompts and trusting the output without a rigorous process behind it. AI native engineering is fundamentally different. Instead of treating AI as a creative assistant, we treat it as part of an engineered system. Context is managed deliberately. Verification is mandatory. Human oversight remains active. What this means is that success depends less on prompting skill and more on operational discipline. The difference between experimentation and production is the presence of reliable engineering controls. That leads directly to the biggest shift in the software development lifecycle. Traditionally, most engineering effort was spent writing code. Design, implementation, and coding consumed the majority of the delivery cycle, while verification occupied a smaller portion. In an AI-native environment, that balance changes dramatically. Now, AI can generate large amounts of code quickly. As a result, engineers spend more time defining context, validating outputs, reviewing behavior, and proving correctness. A good way to think about it is this: generating software becomes easy, proving software becomes hard. The new bottleneck is confidence. To understand how confidence is created, we need to examine the flow of context through the system. This slide introduces one of the most important concepts in AI native engineering: context engineering. AI quality is directly tied to the quality of information it receives. Think of this funnel as a process that transforms raw organizational knowledge into focused, actionable context for an agent. On the left, we have architecture diagrams, requirements, standards, documentation, and business rules. These are filtered, organized, and condensed into the information that an AI agent actually needs. The result is higher accuracy, fewer hallucinations, and more predictable outcomes. In many ways, context engineering becomes as important as software engineering itself. Next, let's look at what happens when context is poorly managed. This slide contrasts two very different approaches. On the left is the anti-pattern, giving an AI a vague request and hoping it produces the right answer. The result is usually confusion, inconsistency, and unpredictable outputs. On the right is the specification protocol. Here, requirements are decomposed into clear objectives, constraints, acceptance criteria, and validation steps. What this means is that we stop treating AI interactions as conversations and start treating them as engineering contracts. When specifications become explicit, outputs become repeatable. Once we have specifications, we need a mechanism to continuously validate them, and that's where the Ralph loop comes in. One of the biggest misconceptions about AI is that larger autonomous runs automatically produce better results. In reality, reliability comes from verification loops. The Ralph loop represents a cycle of planning, execution, review, and correction. Rather than allowing an agent to run unchecked for long periods, we introduce frequent validation checkpoints. A good example of this is reviewing architecture decisions before implementation begins instead of discovering issues after deployment. Small feedback loops dramatically reduce risk. This principle becomes the foundation for the architecture we're about to explore next. This slide presents an AI-driven version of the software development lifecycle. Notice that AI is involved across planning, implementation, testing, review, and documentation. However, each stage has clearly defined responsibilities and validation criteria. The key idea is not replacing engineers. The key idea is augmenting each phase with specialized AI capabilities while preserving accountability. For example, one agent may focus on implementation, while another focuses exclusively on testing or documentation. This specialization leads naturally to the concept of multiple collaborating agents. Let's look at that architecture next. Instead of relying on a single AI agent, AI-native organizations increasingly use agent swarms. Each agent has a specialized role and often challenges the work of other agents. For example, one agent may generate a design while another attempts to identify flaws, security risks, or missing requirements. This intentional friction improves quality. A good analogy is a strong engineering team where architects, developers, reviewers, and testers challenge each other's assumptions. The goal isn't speed alone. The goal is trustworthy outcomes. Now let's examine how organizations mature toward this operating model. AI-native transformation doesn't happen overnight. This maturity model illustrates the progression. Most organizations begin by using AI for individual productivity improvements. Next, AI becomes integrated into team workflows and development processes. Eventually, organizations reach a stage where AI participates as a structured component of the delivery system. The important lesson here is that maturity is not measured by the number of AI tools adopted. It's measured by operational integration, governance, and reliability. The next slide explores where engineers create the most value within that journey. As AI automates routine activities, engineering value shifts. Tasks such as boilerplate implementation and repetitive coding become increasingly automated. Human engineers create value through design thinking, system architecture, strategic decisions, trade-off analysis, and innovation. What this means is that engineering careers become more focused on judgment than execution. The best engineers won't necessarily be the fastest coders. They'll be the best orchestrators, reviewers, and decision makers. Understanding this shift is critical because mistakes at AI scale can be extremely costly. Let's look at some real-world examples. This slide serves as an important reminder that AI mistakes happen at machine speed. Several incidents show how unchecked AI systems can introduce security vulnerabilities, expose sensitive information, or generate dangerous recommendations. The lesson isn't that AI is unsafe. The lesson is that AI amplifies both good and bad engineering practices. Poor governance scales quickly. Strong governance scales quickly too. This is why guardrails are not optional in AI-native systems. Let's examine what those guardrails look like. A successful AI-native organization combines technical controls with organizational controls. Technical guardrails include identity management, permission boundaries, validation systems, and security enforcement. Organizational guardrails include policies, review processes, accountability structures, and escalation paths. A good example is ensuring that no AI agent can deploy production changes without satisfying predefined approval requirements. Guardrails create safe autonomy. Without them, scale becomes dangerous. Even with strong controls, however, human expertise remains essential. That's the focus of the next slide. AI-native engineering does not eliminate human expertise. In fact, it increases the importance of experienced engineers. Humans provide context, judgment, ethics, prioritization, and accountability, capabilities that AI still cannot reliably replace. The most effective model is partnership. AI handles speed and scale. Humans handle direction and responsibility. What this means is that engineers evolve from builders into orchestrators of intelligent systems. That evolution brings us to the final vision of the engineering role. Let's conclude with the future state vision. The engineer of 2026 is no longer defined primarily by the amount of code they write. Instead, they coordinate multiple AI agents, manage workflows, define specifications, establish guardrails, and ensure quality outcomes. Their role resembles an orchestra conductor more than a traditional programmer. They combine technical expertise with systems thinking, leadership, verification, and strategic decision-making. The organizations that embrace this model will achieve extraordinary leverage. The central message of this presentation is simple. AI native engineering is not about replacing engineers. It's about elevating engineers into higher value roles where human judgment and AI capability work together as a single system.
वीडियोस बनाने हैं फिल्मोरा है ना।